Hello class, Dr. Foley. This will be our first video lecture covering chapter 1. These videos could get pretty long, so I'll try to go through this fairly quickly. As you know, we're supposed to meet, I think, 90 minutes a week. So I think these videos might be longer than that, but what I did earlier in the summer was make these outlines, and because I thought we were going to be meeting in person, so I was going to give you these outlines that I've made for several of the preliminary chapters. And I put so much work into them, I thought, well, geez, now what am I going to do with them? I'm still going to walk you through these, just filling in the blanks. I left a lot of blanks that you were going to fill in with me as we talked about this in person. So at least for the first probably 4 chapters, I'm going to use these outlines I've created because I did put a fair amount of work into them, and we'll get through the material that way. I'm kind of following the book page for page, so I'll add a little bit of extra material from other sources, YouTube videos, maybe showing you some simple demonstrations here on the camera. But most of what we're going to do for the first several lectures is just going through these outlines together. So the first chapter of any general chemistry course is going to give you the basics. How do you talk about chemistry, the terms you need to use, and that goes for any science, really. You're going to learn a lot about, how do we classify matter. We'll talk about physical versus chemical changes. We'll talk about not only the qualitative things like that, but the quantitative skills you should have. Making measurements, what is a measurement, learning about the metric system, and how do you treat numbers in science and in experiments. It's not just blindly using the math. We have to have some rules to follow so that we can express our answers correctly. And you've probably heard that before. That's called using significant figures. So let's just go through this outline. This is probably going to take at least a couple hours to get through this chapter. So with a video, you can pause it and take a break. I don't expect you to sit down and watch these from beginning to end in one sitting, unless you really want to. But you don't have to. You can pause it and take a break. The goals of this chapter, again, as I've said, are to discuss what chemistry is and why it's important, to classify matter, to learn the language of chemistry and other sciences, learn about scientific units and measurement, and then finish the chapter talking about unit conversion and make sure that you can understand how to convert units, because that's the skill you'll use in the entire course. So there's some figures I've taken from the textbook. Chemistry is, one of the central sciences, we call it. It pretty much influences everything, every other science that we know of, including physics and biology. Physics and chemistry and biology are probably the 3 main sciences that everything else kind of is a subset of, so to speak. But chemistry is in foods, soaps, plastics, gasolines. After this course, hopefully you'll have a better understanding of the world we live in, and why things might happen the way they do. But we have to review a lot of terms first. Chemical substances and processes are essential for our existence, providing food, keeping us clean, healthy, making electronic devices, etc. Chemistry is literally everywhere in our world, and really the entire universe. But the laws that I'm talking about and the patterns that we see on Earth, pretty much as far as we know, would apply anywhere in the known universe. So they're universal laws. In my opinion, really, there are only 2 types of chemicals. People always say, oh, it's got chemicals, they must be bad. It must be unhealthy. Well, that's not necessarily true. There's really only good chemicals and bad chemicals. Everything is a chemical, really. Let's think of some examples of chemicals that you use every day or come across every day. Water is a chemical. Now we're gonna also learn about how to name these things. Oxygen, the air we breathe, oxygen is a chemical. Sugars are chemicals. Plastics are chemicals. Soaps, there's literally millions of them. Proteins are chemicals. It just goes on and on and on. So the first section of your textbook is titled Chemistry in Context. Before I move on with that, let me just show you the periodic table. So this is, again, the entire course in chart form, essentially. Every known element that makes up our world and the entire universe is in this table. Now, you're going to learn patterns that exist in this table. You probably already know some of these patterns, but we'll review them again. So that's why they call it the periodic table. Periodic just means that there's repeating patterns that we see. And we've organized these elements in these rows and columns for very good reasons that we'll talk about in this class. So the goals are also I'll just give you a little historical background on chemistry, give you some examples of chemistry in everyday life, describe the scientific method. I'm going to show you a video on how to do that because I think other people can explain it better than I can. Differentiate among hypotheses, theories, and laws, etc., etc. So some of you might be wondering, what is chemistry? Well, technically, if you looked it up in a dictionary, chemistry is the study of the composition, so that's what things are made of, the properties, so what do we observe about these compounds and elements, and the interactions or reactions that matter undergoes. So the next logical thing might be, well, what is matter? That's a pretty general term. People have been thinking about what matter is for thousands of years. The Greeks thought matter consisted of just 4 elements: earth, air, fire, and water. Very simplistic view of the world. Alchemists in the medieval times, 15, 16, 1700s, actually attempted to convert base metals, which were common metals like iron and copper, and they tried to turn them into noble metals. They especially were trying to convert the element mercury, which has the symbol Hg, into gold, which has the symbol Au. And they tried and tried and tried, but we now understand that that is impossible. You cannot convert one metal into another by chemical means. You can do it through physical means like nuclear reactions, but you can't do this. This is not possible by chemical reactions. Chemical reactions are lower energy than what we would call nuclear reactions. Nuclear reactions are what takes part in when an atomic bomb or a hydrogen bomb explodes. That's not a chemical reaction. Moving on here. I will cover that in a second here. But this is a figure from your book. I know you can, if you can't see these clearly in the video, you can go to the online textbook. These are figures directly out of the online textbook. This just shows a work around 1518 of an alchemist, what a laboratory might have looked like back 400 years ago. But it was more considered magic instead of science. They didn't really know a lot about chemistry like we do today. So they were like I said, trying to convert other elements into gold, which they were never successful at it. But through a lot of experiments over the last, we've come a long way in the last 100 or so years. We've learned a lot about matter, compounds and elements that have provided us with all the materials that we just take for granted today. Chemistry is interconnected to a vast variety of other topics. I'll show you a little chart of just within chemistry there are several branches, but chemistry is called the central science because it pretty much influences everything else. Since chemistry is the study of matter, and matter is essentially everything, it is you have to know a little chemistry to pretty much do anything in the science, whether it's physics, even math. Um, Chemical engineering is really just applying chemistry to industrial processes and making chemicals on a large scale. Medicine and biology, of course, you have to know some chemistry to understand proteins and fats and how enzymes work. Toxicology, environmental science. Toxicology is dealing with toxins and how the body processes poisons and things like that. Geochemistry, dealing with geology, rocks and minerals. Agriculture, dealing with fertilizers. It just goes on and on and on. So chemistry is really central to all these other disciplines. Now, within chemistry, I made this little just to show you how complicated this can get. There's branches of within chemistry. It just isn't one science called chemistry. Even in any, that really goes for any science, physics, biology. But in chemistry, we have what I studied in college was organic chemistry, which is the chemistry of carbon. So by the end of the course, you'll understand what these funny looking drawings really are. Those are organic molecules made of carbon and alcohols. And the other main branch of chemistry dealing with everything else besides carbon is called inorganic chemistry. Molecules like water and sodium hydroxide, which is the stuff found in Drano, metals, and catalysts, which we use to make other catalysts are used to make chemical reactions speed up. But that's inorganic chemistry. So if you look at a periodic table, you'll see that organic chemistry really just deals with this one element, carbon, with some hydrogen thrown in and some nitrogen and oxygen and sulfur. These elements right in here is pretty much all of organic chemistry. Organic chemistry is really the part of biochemistry. You can't understand biochemistry, which is the organic chemistry of living things. You can't understand this topic without a good foundation in organic chemistry, because all living things, the chemistry of life, is based on carbon. We are based on carbon. We're made of proteins, carbohydrates, and lipids. Those are the three main compounds that make up living tissue. And then there's analytical chemistry, which is the science of analyzing things and determining chemical composition. You'll see we have these funny looking terms, GCMS, NMR, acid-base titrations. You're going to do an acid-base titration this semester in lab. That's just testing, or that's just figuring out the concentration of either an acid or base by doing a carefully measured experiment. NMR is related to MRI in medicine. It uses magnetic fields to look at the inside of our body. NMR uses magnetic fields to look at molecules. And then there's physical chemistry, which is kind of like physics and chemistry combined. It talks about we're gonna actually discuss these strange-looking figures here. This sort of dumbbell-shaped object here I've highlighted in red, or this flower-shaped object. Those are called atomic orbitals, and they're a part of science called quantum mechanics, which is really just the study of electrons and how they behave in molecules. We're only going to look at very simple molecules, because once you get to even molecules that are like this, which in the grand scheme of things are pretty simple, but we have a hard time really predicting how these behave, how the electrons behave in these molecules. But the principles that we use for simple molecules, we believe are just can be applied to anything as complicated as a protein or even DNA. So that gives you a little idea of what chemistry is. Why is chemistry important to us? Well, I'm sure you already know the answer, but with a knowledge of chemistry, you can better understand the foods you eat, how we digest food, the things we use. Polymers are plastics that are used literally everywhere. This desktop I'm using is not really wood. This is a plastic made to look like wood. It's a polymer. They're used in our clothes, our cookware, our credit cards are made of plastics. Plastics come from crude oil, which comes from deep underground, which is called fossil fuels. Refining crude oil into gasoline and other products is based on chemical principles. Without crude oil and gasoline, our world would literally stop. So chemistry is key to a lot of things. What are some other examples of chemistry in our lives? I was going to ask you to, I want you to mentally kind of think about these things as you're watching these videos, but I thought of a few. Like I said, not only do we digest food, but to eat the food, we have to first cook it. Those are chemical reactions. The synthesis of drugs is useful. Especially now with COVID-19, we're trying to come up with vaccines, which is essentially a mixture, complicated mixture of chemicals and drugs. Extracting metals, extracting precious metals or any metal from their ores is a application of chemistry. Electroplating jewelry. These are just some of the ones I came up with off the cuff. That's an example of chemistry in your daily life. Winemaking and brewing, those are based on chemical principles. You can't make wine or beer without knowing something about chemical reactions. As we proceed through this course, you're going to discover that there's many different examples of changes in the composition and structure of matter. We're going to learn how to classify these changes in matter and understand how they occur. And then we're going to talk a little bit about the changes in energy that accompany these changes in matter. It's called the law of conservation of energy. Many of the theories and scientific laws we're going to discuss were formulated and perfected using what's called the scientific method. So everything we really know today is a result of this method. Now, there isn't one correct answer for what the scientific method is. I'm going to show you a video or splice a video into this lecture here that I think better explains what it is. But chemistry is a science based on observation and experimentation. That's really the scientific method. You make observations, you come up with a hypothesis, which is just an educated guess, which is a tentative explanation of observations. And then you do some experiments. The laws of science summarize a vast number of experimental observations. So there's this diagram in your book. It might be hard to read in this from this camera shot, but you make observations, you form a hypothesis, you perform experiments. It's kind of like a cycle. And then if your observations agree with your hypothesis, then your hypothesis kind of gets support scientifically, and it might become what's called a theory, or it might even become what's called a scientific law. So if I had to summarize just in a few simple steps, you observe something. You say, okay, why does that something happen? So you take an educated guess. Well, it's called a hypothesis, but it's really just an educated guess based on observations that you might have made about some natural phenomenon. And then, but you got to test that hypothesis. You don't know if your hypothesis is correct. So science is based on testing. You have to test it. But what we call testing a hypothesis, we call that an experiment. You do some experiments. You design some experiments so that you can test to see if your educated guess about what you're observing is correct or not. And when you do experiments, you watch what happens. So you make observations. Does something explode? Does the color change? Does it generate heat? Does it cause some biological reaction? There's millions and millions of possible experiments that have been done. And then after you make your observations, you ask yourself, was your hypothesis correct? If it was correct, then as I said, you can sort of add that to the body of scientific knowledge. You contribute to it. and your hypothesis might become a theory, or it might become what's called a scientific law. Now, why don't you watch this video that I'll splice in right here with the guy. His name is Neil deGrasse Tyson. He'll give you an everyday example of how this scientific method can be applied. So I'll show you that now, and then we'll continue the video.
There was an incident in Pasadena, California. I was there. I don't drink much coffee. I don't have a relationship with caffeine, but every now and then I'll be delighted to have a nice cup of hot cocoa. And I went to one of these coffee houses, with the chalkboard out front. And so I had, the kind I'm talking about. They're all over Brooklyn. You trip on the chalkboards in Brooklyn. So I'm in there, I order hot chocolate, and I ordered with whipped cream, of course, right? And it comes to the table, and there's no whipped cream. And I said, I ordered this with whipped cream. And they said, oh, we put it on. And I said, well, where is it? Oh, he said, it's sunk to the bottom. I then said, either the laws of physics that apply everywhere in the universe are suspended in your coffee shop, or you didn't put whipped cream on my hot cocoa. And he looked indignant. Really? Now, to his credit, rather than continue to argue with me, he intended to prove me wrong. So he went into the kitchen, brought out the whipped cream, scooped it up, popped it in my hot cocoa, and it bobbed once and floated atop. And there it was. Did you invite us? Of course, whipped cream has to float. Because, first of all, before it was whipped cream, it was cream, okay? And old-timers remember, what does cream do in unhomogenized milk? It floats to the top, and you skim off the cream, leaving behind skim milk, okay? This is how that works. Now, you take the heavy cream and then whip it, putting air into it. It is not going to sink on any known liquid devised by man, okay? So, all right. So here's my point. The lesson there is, yes. I'm a fan of the edict. If an argument lasts more than 5 minutes, then both sides are wrong. I think that applies maybe 85% of the time, but it's a good rule. It's a good tenet to carry with you. Now watch. This is how science works. One researcher comes up with a result, and that is not the truth. No. A scientific emergent truth is not the result of any one experiment. What has to happen is somebody else has to verify it. Preferably a competitor. Preferably someone who doesn't want you to be correct. Such as my waiter. He went out to prove me wrong and got the same result that I had declared. We can call that the beginnings of an emergent truth about whipped cream. Now we need someone to do it in Asia and in Europe, and then you get a trend, and you can then declare that a consensus of observation and experiments has emerged in the scientific community. Whipped cream floats on hot chocolate. And that waiter today is getting a PhD in points.
All right, so as you saw in that video, he was talking about questioning somebody who said that they put cream in his coffee, and he made an observation that clearly it wasn't there, and so he tested his hypothesis. He pretty much followed this pattern by just by what you were by his experience in that coffee shop. So it really, you've used the scientific method your whole life. You just didn't realize it was the scientific method. Science is just a way of looking at the universe and explaining phenomenon that we see. It's just explains everything really, or I shouldn't. It tries to explain things. So we have these things called theories, which currently are our best way to explain things. A theory does not mean we're absolutely right. A theory can be tested. It just explains, why something happens. Um, but it doesn't necessarily mean it's true. We might find years down the road that the theory was wrong. Now, there's these things called laws, scientific laws, which are more like math equations. Laws are just a statement of fact, so to speak. So we have the theory of relativity is just Einstein's way of saying, how does time relate to space? It's a theory. We don't know if we're not 100% sure it's true, but all our observations that we've made and all our experiments we've done provide support that his theory is correct. But 100 years from now, they might find that it was completely wrong. So it will have to be changed or completely abandoned. There's the theory of evolution. There's the, I know a lot of laws, the law of gravity, explained by Isaac Newton, the ideal gas law. The best way I can explain these is ideal gas law and law of gravity are equations. The ideal gas law, which we'll talk about this semester, looks like this. It's PV equals nRT, relating pressure, volume, and temperature of a gas. The law of gravity is somewhat complicated. That's more of a physics equation that we don't really use in chemistry. The law of conservation of energy, the law of conservation of mass, which is a big part of this class where we'll talk about chemical reactions and how we can actually predict how much matter is being transferred from reactants to products. It's really not that complicated. It's amazing how simple chemical reactions really boil down to just ratios and numbers. But that's really the difference between a law and a theory. And also I want to splice in another video that kind of summarizes this. So I'll show you that video right now.
Scientific theory versus scientific law. It is important to understand the similarities and differences between a scientific theory and a scientific law. Both scientific theories and scientific laws describe something that has been observed in nature. They both require many observations and experiments, and they both must be accepted by the majority of the scientific community. However, scientific theories are not laws, and they are not treated the same as laws. Unlike a theory, where evidence changes, a law will never change. In science, a theory is a widely accepted explanation supported by abundant scientific evidence. Theories are not just ideas or guesses about how something works, and theories are not just opinions about a concept. For science to prove a theory, scientists must conduct extensive tests and experiments. A theory must be supported by tremendous amounts of scientific evidence, and it must go through peer review and retesting. Even if a theory is proven, it is subject to change in the light of new evidence. This is the best way for science to evolve and change. In this way, scientists can use theories to build upon the evidence and ideas of other great minds. One good example of a theory that has evolved over time is Newtonian mechanics, first theorized by Isaac Newton in the 1600s. This theory explained the movement of objects, both on Earth and in space. Using Isaac Newton's work, Albert Einstein perfected the theory, renaming it the theory of special relativity. Einstein's new theory put a twist on the Newtonian theory, allowing us to measure objects in reference to space and time. Einstein even upgraded his special relativity theory to a more current version that we use today, the theory of general relativity. Scientific laws are different from scientific theories. A scientific law is a description of a fact that is completely accepted in the scientific community. A scientific law does not change, and if it is refuted, not only does the law become false, but all science that was based on that law also becomes false. Laws state that something in the natural world happens, but they do not necessarily explain how or why. The law of gravity, for instance, states that all objects have a force of attraction for each other. This law explains what happens, but not how it works or why. Theories attempt to explain the how and why. When trying to decide if something is a scientific law or scientific theory, ask yourself this question: does it explain what happens, or does it explain how and why something happens? If it explains what happens, you are talking about a law. If it explains how or why something happens, you are talking about a theory.
So now that we've reviewed a little bit about the scientific method and what theories and laws are, let's move on to more chemistry-related topics. So your book talks about how we look at the universe from what's called a macroscopic perspective versus a microscopic versus a symbolic perspective. They call them domains. Well, all they're really talking about is going from our everyday experience that we see with our eyes down to what microscopes and more sophisticated scientific instruments can see, atoms and molecules, called the microscopic world of cells and atoms and molecules. But chemistry is, we have to have a symbolic way of expressing things. If we didn't, it would be incredibly cumbersome and complicated to explain just a simple chemical reaction. It would be very difficult just to explain what a water molecule is if you didn't have symbols to summarize what water is. So this picture in your book, this figure 1.5, is just showing you the difference between the macroscopic domain, which is the realm of everyday things that we can see, ice and water and clouds and air. I know you can't see air, but we know it's there. But that's what we can directly observe with our senses. But on a microscopic level, the domain of chemistry that's microscopic is picturing things as molecules and atoms. Only in the last couple hundred years have we really come to understand that matter was actually made of atoms, which combine to give you molecules, and molecules combine to give us living things, tissues and organs and things like that. So it's just a level of complexity that increases from fundamental elementary particles all the way up to living things like you and me. But they're all based on chemistry and chemical principles. The symbolic domain would be expressing water as H2O. So we see the macroscopic things would just be water as liquid, gas, or solid. That's what we can see with our eyes. Ice, liquid water, water vapor. But on a microscopic level, we know that water is a V-shaped molecule, which we express symbolically as H2O. Well, we really can draw it like this, as a little V-shaped molecule. Those are symbols. So we're going to discuss a lot about, especially at the beginning of this class, how to write these simple molecules, what each symbol means, and there's a lot of information that's buried within these simple structures. But whether water behaves as a gas or a solid, ice, or a liquid, the molecules never change. It's just how close the molecules are together explains the difference between liquid, solid, and gas. But the water molecules themselves never change. They just make up collectively the solid, liquid, or gas phase. I'm just trying to organize my notes here. Please bear with me for a second. So since chemistry is the study of composition and changes that matter undergoes, let's talk a little bit about matter. And that's just a generic term. So our goals are to describe the basic properties of each physical state, solid, liquid, and gas, distinguish between mass and weight, apply the law of conservation of matter, which is also called the law of conservation of mass. Conservation. That's an N, sorry for my sloppy writing here. Of mass. Now, mass and weight are not the same thing, so we'll clarify the difference between the two. We want to clarify matter as an element, compound, or mixture of some sort, and give you some examples of atoms and molecules. So matter is just anything that occupies space and has mass. So that's the main difference between mass and weight, is that mass never changes. It's a constant. And we'll learn what the symbol is for mass later on. Weight is not a constant. Weight is not constant. Weight can change depending on where you are. And we know that is true because of gravity. Mass is really another way of expressing, it's really just saying how many atoms are in an object. That never changes. And there's a famous equation that Einstein, his theory of relativity, you've probably heard it, it's a famous equation, E equals mc squared. It's really, that's a law. That's the law, that's one of his laws, E equals mc squared. Matter and energy are interconverted. Mass can be changed into energy, and energy can be changed into mass. And that's a big part of this class, understanding how we can use reactions to generate or consume energy. So as you know, there's three common states of matter. A solid is rigid and possesses a definite shape, so that could be like an ice cube in this flask. It doesn't take the shape of its container. It has a constant, definite shape. A liquid will flow and takes the shape of its container. So no matter what you put it in, it just adopts the shape of its container. But the molecules and atoms that make up a solid, liquid, or gas aren't changing. All that's changing is the space between the atoms and molecules. They're very closely spaced here. They're a little bit further apart here, so they can kind of slide over each other. That's why we experience that sliding of molecules and atoms over each other as a liquid. Or they can behave as a gas, which is the highest energy state of matter. And a gas will just completely fill its container. It takes both the shape and volume of its container. And really the only thing that separates a solid, liquid, and a gas is temperature. So solids will exist at low temperature, and gases will exist at high temperature. I'm probably not telling you anything that you already don't know. This chapter is more just, I hope, is just a review of a lot of concepts that you've already sort of learned in other classes. But we can't move forward to more interesting things until we've covered this. Now, believe it or not, there actually is a fourth state of matter, and it's called plasma. I know you guys have heard of plasma because of plasma screen TVs, which are a relatively new technology. But plasma has been around, and we've understood it for hundreds of years. It has unique properties that are different. It's a gas, but it's a little bit different. It's actually electrically charged. It's a charged gas. Some natural examples that are found, and plasma is always generally found in a high temperature environment. Some natural examples of plasmas are stars or lightning. Believe it or not, lightning is electrically charged particles traveling through the air. It's like an electric current traveling through the air. When you see a bolt of lightning, you're not really seeing, you're seeing the air, you're seeing friction in the air, which is such a high temperature, it's causing the atoms of the air and the molecules of the air to glow white hot. But you're not seeing the electrons. The electrons are actually causing the air to glow. Some man-made examples are plasma screen TVs, or you might have seen those plasma spheres where you can touch it and the electric current seems to follow your finger around wherever you touch the sphere. That's a plasma. We use plasma torches in welding. Plasmas are incredibly high temperature. The temperature of a plasma torch can reach about 28,000 degrees Celsius. So incredibly high temperatures can be achieved with plasmas. But in chemistry, we're gonna concentrate on solid, liquid, and gas because chemical reactions are much lower energy than what's going on here, even though that is a chemical reaction. But that's not an everyday chemical reaction that we would run into. So let's talk a little bit more about mass and weight. Mass is a measure of, as I said, as the amount of matter in an object. The amount of matter in an object. Weight refers to the force that gravity exerts on an object. So the difference, you can write a simple equation that relates weight and mass. Weight is equal to the mass of an object times gravity. That's why we weigh less on the moon. So an object's mass is the same on Earth and on the moon, but its weight is different. And that's because the gravitational pull of the moon is about 1/6 the gravitational pull of the Earth. That's why I weigh about 180 pounds here on Earth. If I traveled to the moon, I would only weigh about 30 pounds. If you've ever watched videos of the astronauts on the moon, it looks like they're bouncing on a trampoline. Well, that's because the gravitational pull on their bodies and on their spacesuits is less than on Earth. We've just evolved to live normally on a planet Earth where the gravity is what it is. If we lived on the moon, we would be very different. So there's less gravity, so the weight is different. There's the law of conservation of matter and mass that we must follow in chemistry. There's no detectable change in the total quantity of matter present when matter converts from one type to another. So I'm talking about a chemical reaction. Any chemical or physical change means that the mass that we can measure before is equal to the mass that we can measure after. So when ice melts, if you measured carefully the mass before the ice melts, it's equal to exactly the mass of the water that's obtained after melting. And that probably seems pretty obvious to you, but it has a very deep meaning, and it helped scientists a couple hundred years ago, help them develop the theories that we use today of how we understand chemical reactions. So a couple everyday examples of the law of conservation of mass and energy is fermentation of alcohol into beer, the mass of the materials that go into the beer, which is water. And if you mix a little yeast and a little bit of barley or rye or rice, the weight of that, the mass of those is the same as the water and the alcohol that's generated from the grain and the CO2. So what I've just written is a chemical reaction, but not in the way I want for you to write one, because that's just way too hard to write. We have to come up with a symbolic way. Car batteries also obey the law of conservation of energy. Pretty much everything does. And so that's kind of a hard concept to grasp, but believe it or not, all the matter that's ever existed on Earth never changes. It's just changing from one form to another. We haven't gained any mass over the last 4.5 billion years. We haven't lost any mass. It's just been converted from one form to another. So let's get more specific. What exactly is matter in a chemical sense? Well, as I showed you earlier, matter is summarized with this table. This is matter, but these are the ingredients that make up matter. You can think of the chemical elements as the ingredients a chef might use in a kitchen. These are all the things we mix together in countless ways to come up with all the different molecules. There are literally millions of molecules that either naturally occur or that we've made in laboratories for drugs and making all the materials that we sort of take for granted. So let's make sure you can understand how we can classify matter. What are elements? Well, symbolically speaking, elements are the symbols you see on the periodic table. There's hydrogen, lithium, and I want you to try to memorize the first 36 symbols. So from hydrogen down to krypton, it would be helpful if you would memorize the symbols and the names, because those are the common elements that we're going to discuss in this class. Hydrogen, lithium, iron, carbon. Now these elements cannot, what distinguishes an element from a compound is that elements cannot be broken down by chemical changes. All that happens to an atom in a chemical reaction is it breaks its bonds with whatever it was bonded to, and it makes a new bond with another atom. But it's hydrogen before and it's hydrogen after. It's iron before and it's iron after. It's just changed what it's bonded to. That's what a chemical reaction is. There are literally, well, not literally, but there are about 100 known elements. I don't know how current this periodic table is. Sorry, I was out of the view there. But most of the common elements are in the first 3 rows. The further down the table you go, the rarer the elements become. But about 90 of these elements occur naturally, pretty much the first 90 or so, all the way up to about uranium. Those pretty much occur naturally on Earth. From hydrogen, helium, lithium, beryllium, boron, etc., etc. There's actually a guy that came up with a song to memorize all these things. You could probably find it on YouTube. Most of the universe, believe it or not, is made up of these 2 elements, hydrogen and helium. Over 99% of the known universe is made up of the 2 simplest elements. The rest of the elements, we believe, were actually made on the insides of stars. So these first 3 rows were made in stars. At least that's our theory. Because why do we know that? Well, let's go back to the scientific method. How do we know, or why do we believe that most of those elements were made in stars? Because that was our hypothesis, and we made some observations. Astronomers have looked at the light coming from stars billions of light years away, and we have instruments that can actually tell us the light coming to Earth through the telescopes. We can tell what the chemical makeup of is. We can tell what the light is made of, and you're actually going to do a lab pretty early in the class that will help you understand how that's done. It's really not that hard to do. But most of those are made in stars. When stars explode, there's tremendous energy, and hydrogen and helium are fused together into more and more complicated elements. And over the last 4.5 to 5 billion years that we've been around here on Earth, most of these elements were made and sort of blown through the universe by these huge explosions called supernovas, and made their way to Earth and make up us, essentially. If you want to learn more, there's a really good website that I think is really fun to watch. I have it on the canvases too. It's called periodicvideos.com. It's a guy in England who has I think he's a professor at a university there. But go to that website, and he has the main page has a periodic table. And you can just click on an element, and he will give you a little video, a little history about that particular element, and they'll show you some fun things about the element. If you watch some videos about these first couple columns, those are really reactive, so you can see some explosions. What you're going to realize is the further closer to the edges you go of the table, those elements tend to be more reactive. The further into the table you go, the elements get more stable. That's why we make money out of elements like copper, silver, and gold, because they're in the middle of the table. They're put there because they're chemically stable. They don't react with a lot of things. Now, that's a general pattern that we've seen, but we've learned to manipulate elements in many ways so we can actually make copper, silver, and gold react. But that's only because we've learned how to do many chemical reactions through experiments. A lot of these elements, especially these down here, these are separated from the rest of the table because they're generally radioactive and they don't naturally occur on Earth. These were man-made elements. So the more common the element, sorry about my sloppy writing, So these are generally, this is the realm of physics, all right, nuclear reactions. We're not going to really deal with these elements down here. We're going to deal more with the elements up here, especially the second row: carbon, nitrogen, oxygen, and fluorine, and chlorine, and phosphorus, and sulfur. Right in here, those are the most important elements, because those are the elements that make up the molecules that are make us, that make biochemical. Here's a little bit more colorful version of the periodic table. As I was telling you, most of the common elements are up in the upper part of the periodic table, especially the first 3 rows. I just want to show you a few diagrams discussing the elements. For instance, this one shows us the approximate distribution of the column elements in nature. For instance, like I said, the entire universe is made up of 91% hydrogen and about 8.75 helium. All the other elements, believe it or not, are less than 1% of everything. And so that's a very low amount. So again, most of the known universe exists as stars, so that's why it's mostly hydrogen. A star is mostly hydrogen gas. On Earth, there's quite a different distribution. There's a lot of silicon and a lot of oxygen. Well, that's because that's sand, and which makes up rocks. There's a lot of aluminum found in minerals, and there's a little bit of iron, some trace elements. There's only about 1% hydrogen, which is present, which would be found in mostly water. But a very different distribution of elements relative to everything. Now, the human body is even a little bit more different. It's got quite a bit of oxygen and quite a bit of carbon, 18%, and quite a bit of hydrogen, because again, we are made of mostly proteins, carbohydrates, and lipids, which are made up of these 3 elements: carbon, hydrogen, and oxygen. We have a little bit of calcium, 2% from what's in our bones, nitrogen for proteins, et cetera, et cetera. So it's interesting that there's such a wide distribution of elements. I want to just show you a few interesting things about some of the elements. For instance, this is carbon. These are the 3 common forms of carbon. Diamond has this shape. These spheres represent carbon. You can see it's got a very rigid structure because each carbon is bonded to 4 other carbons. That's what gives it its durability. Graphite, which is just pencil lead, is another form of carbon. It looks like this. It's these 6 membered rings of carbon, which gives it very different properties than diamond. And about 30 years ago, they discovered a new version of carbon, not the soccer ball, but this one here. It looks like a soccer ball. It's got 5 membered rings, pentagons, and hexagons. These spheres are all carbon atoms. That was that molecule was named after a famous architect, so they called it, whose name was Buckminster Fullerene, but they called it Buckyball for short. It's actually 60 carbons. It's C60. That spherical ring or spherical structure is 60 carbons. Same pattern as a soccer ball. That's pretty crazy. But that is there's a lot of research going on with that particular form of carbon. Iron, another interesting element that's found a lot in nature, is useful in hemoglobin. It's found in red blood cells. This is a picture of a hemoglobin molecule. There's an iron atom in each part of the protein. This is a protein made of 4 parts. In the center of each of these 4 subunits is an iron atom and some other organic molecules. So iron, that's why we need iron in our diet, so that we can transport oxygen easily. Copper is found in many places. Piano strings, the Statue of Liberty. Here's a piano string. I have a business where I work on pianos, and this is what copper is. You know, it looks like a shiny penny, but copper and metals can be formed into many different shapes. One property of metals is you can pound them into sheets or form them into wires. That's why electric circuits are made out of metals like copper and silver. But this is many hundreds of windings of copper on a piano string. This is piano strings can be up to 8 feet long. So this is one application of, or how we can use a metal like copper. Copper can also be used to make brass instruments. When you mix copper with zinc, you get brass, a nice shiny alloy. So we're going to talk about how we classify materials like this. Another interesting element is silver, and silver is used in jewelry. But believe it or not, people have actually ingested silver, and this poor fellow here has a disease called argyria, which causes his skin to turn blue. He actually took a lot of what's called colloidal silver, which is elemental silver suspended in a solution, and it was thought to have health benefits. But if you take too much silver, your skin actually turns blue. The silver deposits in your skin cells. I'm not sure about the health consequences of it, but that's an irreversible effect. His skin will never go back to normal. So before you continue with this video, I encourage you to go watch the video I put on Canvas that is narrated by Carl Sagan. It's just a short video where he discusses the chemical elements. And he was a famous astronomer, had a series back in the 80s called Cosmos. You might have heard of it. Very good series. I encourage you to look it up on YouTube or Netflix. But he talked a lot about chemistry as well. So that might be interesting for you to watch before you continue with this discussion. But let's go through some definitions. Elements are pure substances that cannot be chemically broken down. Elements are not as common as compounds, but here's a few examples of some elements. Here's carbon. I use this for some applications when I need to lubricate things, but if I just put some of this on my finger, you'll see it's pencil lead. It has a shiny, slippery feel to it. Turns your fingers black as well. But that's just like charcoal. It is used as a lubricant, but that's because of its atomic and molecular structure, which we'll discuss later on. Money we make out of elements. This is copper in its pure form. Steel wool is just iron, mostly iron. That's a chemical element. How is that different from a compound? Elements cannot be broken down any further. They are made up of atoms bonded together. Compounds, on the other hand, are pure substances like elements, but they can be broken down by chemical means. What are some examples of compounds? Well, there's millions of them, but there are two or more elements chemically bonded together: carbon dioxide, water, iron oxide. If you allow the steel wool to rust, it will combine with oxygen to make a compound called iron oxide, which has the formula Fe2O3. Ordinary water is a compound made up of hydrogen and oxygen, as you probably know, H2O. Now, hand sanitizer, it looks like water, but this is a compound. This is a mixture. How do you tell them apart? Well, we have testing methods that make that pretty clear to us, but this is what you're going to learn how to predict and understand in this class. The key point is that the properties of compounds are different from the uncombined elements. The elements that make up water, hydrogen and oxygen, are very different from water. They're both gases. You combine two gases and you get this clear, colorless liquid. That's pretty crazy. Hydrogen gas H2 is very dangerous, whereas oxygen is necessary for life. Your book shows a diagram where mercury, what's called mercury oxide, which is actually a red powder. It's probably hard to see in this picture here, but it's a red solid. It's an ionic compound like table salt. If you heat that up with a lot of heat, it actually decomposes into elemental mercury, which is silver, which is used in thermometers. It's one of the only elements that's a liquid at room temperature. The other one is bromine. And then oxygen is a colorless gas. So the physical properties, the macroscopic properties that we observe are very different for different elements. When you make salt, you combine two rather toxic elements, sodium and chlorine. but you make sodium chloride, which is used in food. So the chemical properties of elements are very different from the chemical properties of the compounds that they are part of. However, most matter exists actually as a mixture. So this hand sanitizer is a mixture. How do you know it's a mixture? Well, if you just look at the ingredient list, you'll see a bunch of rather strange sounding things. That's a mixture. A mixture is composed of two or more types of matter that can be present in varying amounts, but can be separated by physical means. What is a physical change? Boiling, filtering, freezing, or melting. Those are all physical changes. They involve changes of state from a solid to a liquid to a gas, or from a gas to a liquid to a solid. The chemical makeup of the substances isn't changing. You're just changing the physical state. So we classify mixtures in two general classes, homogeneous mixtures and heterogeneous mixtures. A homogeneous mixture has the same composition or uniform composition. You're probably familiar with the more common way of describing a homogeneous mixture, which is a solution. A solution is just a mixture of two or more things combined. There are many examples of homogeneous mixtures. Homogeneous just means it's uniform. Heterogeneous, the prefix hetero just means that there's different things involved in the mixture. Some examples of a homogeneous or solution is air, if it's filtered, salt water, gold, silver alloys, which are used in jewelry, like my ring is not pure gold. It's a mixture of gold and silver, but that, believe it or not, is a mixture or a solution. It's just a solid solution. Windshield washer fluid is a solution. A heterogeneous mixture has a non-uniform composition. So how do you tell them apart? Well, it's very, very easy. So for instance, I can take let me just take this glass of water and so that's a pure substance called a compound. And if I take some table salt, which is another compound with the formula sodium chloride, I can make a mixture like seawater. So if I just pour this in here, a bunch of it, I'm combining two pure substances into what's called a solution. So if you stir this up, you know that it's going to completely dissolve. What you're going to do in lab, the first lab that you're going to do, or that you may measure the density of an egg, is you're going to do something like this, but you're going to dump a lot of salt into water to make what's called a saturated solution. So that's a little cloudy, but it would eventually clear up. So that's now I've made a homogeneous mixture or a solution. If I take food coloring, which is another compound, I can add a drop to that and it'll turn a nice pretty blue color, but that is still just a solution. How do you know it's a solution? Because it's clear, you can see through it. So that's a homogeneous mixture. This would be an example of a heterogeneous mixture. This is a rock of some sort, but you can see that the composition of the rock is not uniform, whereas this is very uniform. No matter where you look, it's a blue, clear liquid, but we know it's made up of more than one component, so we know it's a mixture as well. This is very different depending on where you look. So this is a heterogeneous mixture. The grain of this table, which is not real wood, but it's simulating wood, wood is a heterogeneous mixture because the composition over here, the grain of the wood, is different from the grain of the wood over here. So it's not uniform throughout. That's the difference between a homogeneous mixture or solution and a heterogeneous mixture. There's no other alternative name for a heterogeneous mixture. You can also tell a heterogeneous mixture easily because you can see different phases. You might see a liquid in a solid or a gas dissolved in a liquid. Soda pop, for instance, would be a heterogeneous mixture because you have gas bubbles dissolved in liquid. Even though the soda might look clear but colored, it's got gas bubbles, so it is a heterogeneous mixture. Some other examples are sand, rocks, pizza, and as I said, wood is considered a heterogeneous mixture. Now, your book has a diagram showing you that as well. Oil and vinegar salad dressing is a heterogeneous mixture because you can see the oil separates from the water. It doesn't have a uniform composition, whereas Gatorade, same color, but it's clear but uniform. That's a homogeneous mixture. So we can break down what I just talked about into a chart like this. So matter, which is anything that has mass, can be broken up into two general classes. Either you have a mixture or you have a pure substance. If it's a pure substance, you can designate it as, can it be chemically broken down into simpler things? If it's yes, then you have a compound. A compound can be broken down. Water can be broken down into its component gases. That's what goes on in a fuel cell. You break water down into hydrogen and oxygen. If the pure substance cannot be broken down chemically, you have an element, which are those symbols, those 110 or so different atoms, which we call the chemical elements. And again, if it is made up of two or more pure substances, you have a mixture, and mixtures are classified as either heterogeneous, which is a non-uniform appearance, or homogeneous, which is a uniform appearance. So some more definitions to go through here. Now, another word for element is atom. The word atom comes from the Greek word atomos, which means undividable or indivisible. Back in the, probably 2,500 years ago, they understood atoms. There was a Greek philosopher named Democritus who actually proposed that atoms existed. He had no ability to do any research. He just used the power of his mind to come up with this idea. But the bad news is that his ideas were very revolutionary and suppressed by other philosophers. Actually, it was the 5th century BC, sorry. But it took about 2,400 years before a man by the name of John Dalton came along and actually supported Democritus's hypothesis that atoms existed by doing some experiments. He did some experiments where he combined various elements with oxygen and did some careful measurements, and he was actually able to come up with a theory, his atomic theory, which we'll discuss in Chapter 2. So as you know, we represent atoms using element symbols. Hydrogen, H for hydrogen, silver is Ag, copper is Cu, copper, etc. As I mentioned in an earlier part of the video, I'd like you to memorize the first 3 rows, hydrogen through krypton. That would make your life a little easier when we discuss naming compounds. Molecules is another word for a compound. So again, we're reviewing with you the language of chemistry. So elements can be called atoms, compounds can also be called molecules. A molecule, by definition, is just 2 or more atoms or elements chemically combined, which are held together by bonds. Now, the bonds that we'll talk about later on can be classified as either what are called ionic bonds, like table salt, or covalent bonds, which are bonds found in substances like water. So as I was saying about compounds, there are literally millions of them. Some of the common ones we've been talking about are sugar, salt, water, rust, carbon dioxide, even ibuprofen, the stuff you take when you got a headache. That is a chemical compound or a molecule. We're going to discuss how to name them later. There are chemical names that follow a system. CO2, carbon dioxide, is a systematic name. But all these other names are common names. So there's a big difference between a chemical name like carbon dioxide and a common name, which we'll discuss. We'll get to it in good time. Here, if you look at an element like gold, for instance, under an electron microscope, this is figure 112 from your book, you actually do see, I don't know if you can tell in the video, but look in the online textbook, you'll see actually tiny little spheres So this is visual proof that atoms actually do exist. They're like pixels on a TV screen. The scale that you're looking at here, when you look at the distance between the center of an atom to another atom, is about 10 to the negative 10th meters. Incredibly small. 10 to the negative 10th meters is what's called an angstrom. It's, I guess, a tenth of a billionth of a meter, tenth of a nanometer. Molecules are viewed very differently than atoms. They're much more complicated. So keeping with this theme that the textbook likes to talk about between the macro view of the world and the micro view of the world, if you take a piece of cotton, and look at it under a microscope, you'd probably see something like this, a single cotton fiber, which kind of looks like a hair. That's magnified 40 times. If you look even further with an electron microscope, you'll see even more detail. It still has the same sort of strand-like, hair-like structure, but there's a lot more detail. If you keep focusing in further and further, closer and closer, millions of times, you'd actually see individual molecules. And since atoms, don't really have colors, we've adopted this system, especially in organic chemistry, where we designate carbon as with a black sphere, oxygen with a red sphere, and hydrogen with a white sphere. So cotton is mostly made out of carbohydrates. That's why you see carbon, hydrogen, and oxygen. If you kept focusing in and zooming in, if you had that sort of ability into the atom, you'd see the pieces of it, the components of an atom, protons, neutrons, and electrons. And then you can keep actually going further and further, but then we're getting into the outside the realm of chemistry. So this is about as far down as we'll go as far as magnification goes on the atomic level. So we often visualize molecules using these colored spheres. Now again, these colors are just made up for our benefit to distinguish different types of atoms. Atoms really, as far as I know, don't have a color. Hydrogen, for instance, is usually drawn as white, oxygen red, phosphorus is orange, sulfur is yellow. These are elements. Elements are not just, they don't exist as just one single atom. Hydrogen actually exists as two atoms bonded together. That's why we call it H2. Oxygen, the oxygen we breathe, is O sub 2. The subscript 2 means there's two oxygen atoms bonded together. We call those diatomic elements. The prefix di means two atoms. Phosphorus is made up of repeating units of 4 phosphorus atoms. Sulfur is made up of a repeating unit of 8 sulfur atoms in a ring. Water is a little V-shaped molecule, H2O, of course. CO2 is a linear straight molecule made of CO2. This is a glucose molecule. Still considered a simple molecule, but it's made of 6 carbons, C6, 12 hydrogens, and 6 oxygens. But these are all these are compounds. These are elements. So make sure you can distinguish between them. Now, to confuse you even more, these are all molecules. So earlier I said that you can call a compound a molecule and a molecule a compound. I guess that wasn't totally correct. A molecule is just, by definition, 2 or more atoms bonded together. So you can have a molecule of hydrogen, but hydrogen is considered an element. Just to confuse you, of course. A compound is 2 or more different elements. So these H2O, CO2, and glucose are called compounds. That would be the proper name to name them, not a molecule. I know that's a little bit confusing. Don't worry, you will get this. Molecules are rearranged during chemical reactions, but the mass is conserved. So if you look, we can decompose water. This is figure 115 from your book. I think it's just, that's a 9-volt battery that you can actually use to, if you put it in water, you can actually break down the water with the voltage from the battery, and you'll see bubbles coming off. The bubbles are hydrogen and oxygen gas. So the water is actually being broken down, decomposed into its constituent molecules. So again, that's a compound. If you really want to get picky about it, water is called a compound. These are called molecules, but they're also called elements. They're diatomic molecules. But they're a molecule because they're made of two or more atoms bonded together. Even a cell phone can be considered an example of a chemistry experiment. There's many different components to a cell phone. There are plastics used in the frame of the phone, which are made of mostly carbon. This long chain represents carbon. This is just a shorthand notation for compounds we'll worry about later. The glass is made of silicon dioxide, sand. The batteries contain lithium ions. That's an inorganic or metal. The microprocessor is made of silicon, which is doped with other elements. Silicon is one of those elements in the periodic table. It's not really a metal, but it's not really a non-metal like oxygen. It's kind of in between. It has properties of both. It's called a semiconductor. Almost 1/3 of naturally occurring elements are used to make a cell phone. So now that we've classified matter a little bit into elements, compounds, and mixtures, let's talk about the changes matter undergoes. So this is a chemistry class, so we are interested in chemical and physical changes. Chemical changes are also called chemical reactions. So some more definitions for you. We identify properties and changes of matter as either physical or chemical, of course. We identify properties of matter as either being extensive or intensive. So what's a property? A property is just something you observe about an object. It might be its color or its density or its physical state or its temperature. Anything you can observe with your senses is considered a property. And then we break properties down into chemical or physical, or extensive or intensive. So let me clarify that for you. A physical property is a characteristic of matter that's not associated with a change in composition. So when you observe a physical property, no chemical changes are occurring. That simply means that the molecules are staying and the compounds are staying together through the physical change. So observing the color of an object or measuring its density, you don't break the molecule or compound down. You're just changing its physical state or observing its physical state. When you boil something, BP is boiling, melting point, freezing point. Those are all measurements or properties that we can observe, but only involve the change of state from liquid to gas, of course. Melting is solid to liquid. Freezing is liquid to solid. We also classify transformations of matter as, we can call them changes. A physical change is a change in the state or properties of matter without any accompanying change in its chemical compositions. So, for instance, your book has a picture of butter melting in on a stove. Well, it's still the melted butter is still, you can solidify the butter by cooling it, and it goes back to being butter. It's still butter. So it's not undergoing any chemical changes. Steam condensing on the inside of a pot, that's just water vapor, liquid water that's evaporated. It's still water. The gaseous water can condense back to water. So the molecules are staying together. Those are physical changes. Compare this with a chemical change. The chemical change is what we're going to concentrate on in this class, observing chemical changes and measuring them. The change of one type of matter into another is a chemical change. So for instance, I can show you a series of pennies. For instance, here's a new penny. Here is a slightly older penny. Here is a little bit older penny, or more weathered penny. Maybe I kind of have those backward. And here's a really old penny. What we're observing here is a chemical change. What's going on here is this penny here has clearly been around a lot longer than this one. This is combined, the copper on the surface of the penny is chemically combined with the oxygen in the air to form this black compound called copper oxide. Now, the Statue of Liberty in New York is made of the same element. If it was new, it would look like that, but it's turned green over the years because a acid rain has combined with the copper to make a compound called copper acetate, which has a greenish color. But this is a chemical change. This is not copper anymore. The black material or deposit is copper oxide. So you've made a new compound. That's the main difference between a chemical change and just a physical change where something melts or something boils. There's many examples of chemical changes. Iron rusting, which we'd represent with a simple reaction like this. So we're going to be talking a lot about chemical reactions and how to balance them. This is not a complete reaction yet. It's just iron combining with oxygen to give you iron oxide, or what we call rust. One of the labs you're going to do this semester is you're going to dissolve copper in nitric acid. And you're going to take the copper through a series of reactions. That's a chemical change, of course, because the copper, when it combines with nitric acid, becomes what's called copper nitrate, a new, different compound. When you burn a match or burn a candle, that's a chemical change because you're taking a compound that contains carbon and hydrogen and combining it with oxygen, and you're making CO2 and water. So you're making new substances from other substances. So that's a chemical change, of course. When fruit oxidizes from enzymes breaking down the sugars, that's a chemical change. You might know chemical changes generally are not reversible. Sometimes they are, but physical changes can be reversible. You can cool water down and the gaseous water will go back to liquid. You can cool melted butter down and it will go back to being solid butter. But it's very difficult to take rust and make it back into iron. That won't naturally occur. You could do it, but you'd have to put in work. It's not a spontaneous process. It's hard to take CO2 and water and make them go back to being candle wax and oxygen. That's very difficult to do, but that's what plants do. Photosynthesis is the opposite of this reaction to give us oxygen. It can be done, but under normal circumstances, chemical changes like this are not reversible. When you cook red meat, the proteins oxidize and denature to make something else. So that's a chemical change as well. Now, how do we identify chemicals? This is a symbol you're going to see when you come to lab next week, or this week when you're watching these videos. You're going to see symbols like this on the building and on doorways that you might go in. Fire departments often need to see these symbols, but this is a way we visually summarize chemical and physical properties of elements. We use this, what's called an NFPA code, National Fire Protection Agency code. The diamond is standardized throughout the world. The red part deals with, I believe it deals with fire hazard. The yellow part deals with chemical reactivity. The blue part deals with the health hazard, and this bottom part of the diamond deals with anything specific or special to that compound. If you see a big W with a line through it, it means it's a reactive with water. Don't have water around that chemical. So if you went into a building where you saw 4s on all these categories, you better be worried, because the higher it goes from 0 to 4. So the higher it is, the more dangerous the chemical is, either with being more flammable or being more toxic or being more chemically reactive. If something has a 4 in the yellow region, it usually means it's explosive. And finally, we divide chemical and physical properties into 2 general categories. As I mentioned earlier, we can either call them an extensive property or an intensive property. An extensive property depends on the amount of matter present. So some examples of extensive properties are mass, volume, or length, area, or heat. So it's pretty easy to understand that the longer an object is, the more area it's going to have, or the more volume it's going to have, or the more mass an object has, the bigger it is, so the more area it might have. That's what an extensive property is. An intensive property of a compound or mixture does not depend on the amount of matter present. so things like temperature, density, or boiling point are intensive properties. You could have a swimming pool full of water, but it would have the same boiling point as a tiny glass of water. Boiling point does not depend on how much water you have. The density of an object, the density of this penny, if I measured it, would be the same as the density of a piece of copper that was a ton or weighed 1,000 pounds. The density is an inherent property of the element. It doesn't change. It doesn't matter on how much of the compound or the element you have. That's the difference between an intensive and an extensive property. Even the periodic table organizes elements according to these certain properties. So let me see if I can find my periodic table here. So as I said earlier on in the videos, we're gonna talk about this. So you should have a periodic table. Bring it to, always have it handy when you're watching these videos, because there's, I'll refer to it a lot. But we've visually organized this table according to the chemical and physical properties of the elements. All these elements here, from this side of the table, are all metals. Oh, sorry, that wasn't in the view, except hydrogen. Why do we put hydrogen, which is a non-metal, which really belongs over here? Why do we put it over here? Because it chemically behaves similar to elements like lithium, sodium, or potassium. So we put it in the first column, even though it is a non-metal, which is over here. So all these elements over here to the right of the staircase are non-metals. These metals are all solids at room temperature, except, of course, mercury. These non-metals have different physical properties and different chemical properties. These are almost all gases at room temperature versus solids. They're all gases except bromine, which is a liquid, and iodine, which is a solid. So what you'll learn in this class is where the element is in the table is going to tell you something about not only its chemical properties, but its physical properties, whether it's a liquid, solid, or gas.